Hello everyone, welcome to your daily physics problem, day number 31. So today we have a scenario. Ignore all the friction and mass of Pauli. What is the force required to make M1, M2, and M relative stationary? It's a pretty easily stated problem and very clear diagram. So I want you to stop the video, try it all. After you try it, come back to the video and show you how I did it. So welcome back guys. First let's understand what it means by relative stationary. So on this graph, we know there are a lot of forces acting on the graph. We have M2G acting on the M2. There's tension force. We don't need a gravitational force M1 and M because they are frictionless. So they are not matter. Doesn't matter. There are also a tension force acting on this direction on the pulley. So the pulley will pull the big mass backward. So we know this diagram, M1, M2 will move downward to the right, and M will move to the left. So relative stationary means those three objects, M1, M, and M2, have to have the same acceleration. So they will be relative stationary. That's what it means. So how are we going to try to approach this problem? Well, let's imagine what will happen if both three systems are, three blocks are accelerating. What will happen? Well, we can see from some intuition of physics. We can write another diagram. We know the tension force should be a little bit bended. The string that holds M2 should be a little bit bended, because the system is accelerating rightward. So there will be an inertia force acting on M2 to the left. There is also gravitational force. There's an inertia force, because accelerating rightward was A. Inertia force opposite to the acceleration, M2A, leftward. And there's F and M. Then we have our tension force again. Then now we can solve for system equation. Let's define this angle as theta. So we have t times sine theta have to equal to m2g. That's in the vertical direction. Horizontal direction is t times cosine theta equal to m2a. Then also from Newton's second law, we know the acceleration of m1 times m1 is equal to t. And they both have the same acceleration, remember. Then we know the acceleration of m. We know m times a minus t times cosine theta have to equal to 0. Oh no, not this. ma plus at plus t times cosine theta have to equal to f. That's the one we need to know, because we know the acceleration of m is also a net force of the force F minus the tension T, and because the tension T acting on the pulley, pulling back to M, and also T times cosine theta will be the pulley because it's being a little bit tilted to the horizontal component, and also pulling back to the big M. So after we have the system equation, we can try to solve it. Now to solve for F, we need to know what is T and what is A. So from the second expression, we know m1 times a equal to t. We can plug it back into our f equation. We have m plus m1 times cosine theta times a equal to f. Then what is cosine theta? From the second equation, we know cosine theta equal to m2a divided by t. And what is t? T equal to m1a. So we know cosine theta equal to m2 divided by ma. Then let's plug it back in to our original equation with m plus m1 plus m2 times a will be equal to f. So now all we need to know is what's the acceleration. So from the fourth equation, we know, not from the fourth, from the relationship between the second equation and the first equation, we know a equal to t divided by m1. And what is t? T equal to m2g, m2a divided by cosine theta, sine theta, and that divided by m1. Then from the trigonometric identity, we can derive sine theta from cosine theta. So we know 1 divided by sine theta just cosecant theta. So we have m2g divided by m1 times cosecant theta will be m1 squared. m1 divided by m1 squared minus m2 squared, all of them square root. And m1 cancel out, so we can simplify it and plug it back in to the equation. So we have m plus m1 plus m2 times m2 divide by m1 squared minus m2 squared, all of them square root, times g equal to f. And that's our final solution. Thank you for today.